So in this section, we're going to talk about isotopes. So it's important to realize that neutrons have no electrical charge. And for a given type of atom or element, the number of neutrons may vary. So atoms that have the same number of protons, that is the same atomic number, but different numbers of neutrons, this will give them different mass numbers, they are called isotopes. So their atomic number is the same, but their mass number is different. And a good example of this are the three isotopes of hydrogen. All of these guys here are hydrogen atoms because they all have one proton in their nucleus. But this hydrogen atom has a total of one particle in its nucleus, that is, it has no neutrons. This guy has a neutron and a proton in its nucleus. And this one has one proton and two neutrons in its nucleus. So most elements occur as a mixture of one or more than one isotope, and they exist in these mixtures are of characteristic proportions. So for example, if we look at the three isotopes of hydrogen, it's overwhelmingly the first one with very small amounts of the second two. If I look at something like boron, then there are two isotopes, and there's about 20% of a lighter one that has 10 particles in its nucleus, and about 80% of a heavier one that has 11 particles in its nucleus. A few elements exist exclusively as only one isotope, and some have, two or three. Some are more closer to like a 50-50 mix of two isotopes. Lithium exists as a 93.7% mixture of two isotopes, so it's kind of all over the place. So some atoms have the same total number of protons and neutrons. That is, they have the same mass number, but they have different numbers of protons. And these guys are referred to as isobars. So here's two atoms here. They both have a total of 14 particles in their nucleus, but this one is a nitrogen atom with 7 protons, and this one over here is a carbon atom with 6 protons. Here are two isobars. They both have 58 particles in their nucleus, but this guy is an iron atom with atomic number 26, and this one is a nickel atom with atomic number 28. So isotopes are atoms that have the same atomic number but different mass number. Isobars are atoms that have the same mass number but different atomic numbers. Most elements exist as a mixture of isotopes, and that mixture will have characteristic proportions. The percentage of each isotope is referred to as the natural abundance of that isotope. So now we kind of turn our attention to how much does an atom weigh. So the atoms that make up, the particles that make up atoms are very, very small, and grams are not a useful way of expressing their masses. So we tend to express their masses in terms of atomic mass units. And this is a relative mass scale that gives us kind of more sensible numbers to work with. So how we came up with this mass scale was we just said that the carbon atom that has 12 particles in its nucleus, what we call a carbon-12 atom, has a mass of exactly 12 atomic mass units. And then every other atom, its mass was computed as a fraction or a multiple of this number. So all an atomic mass unit is just 1/12 the mass of a carbon-12 atom. So in the periodic table, normally written below the element symbol, will be given an average atomic mass. And this average atomic mass is a weighted average that takes into account the proportions of all of the different isotopes that are present in a natural sample of an element. So if I look at something like boron here, we saw earlier that boron has two isotopes, a lighter one with 10 particles in its nucleus, and a heavier one with 11 particles in its nucleus. The lighter one, unsurprisingly, has a mass of about 10 AMU, and that comprises approximately 20% of the atoms in a natural sample of boron. The heavier one has a mass of about 11 AMU, and that comprises about 80% of the atoms in a natural sample of boron. To compute the average atomic mass, taking into account the relative proportions, what we do is we take the mass of an isotope, we multiply that by the fraction of that isotope, which is simply the percentage divided by 100. We do that for every isotope, and then we add those numbers together. So it is the mass times the fraction for every isotope, and then we add those together. And if we've got our answer correct, it should agree with what is given in the periodic table. Now, this answer here of 10.811, it makes sense because our answer should be, our average should be a lot closer to 11 than what it is to 10, because we have mostly 11 with just a little bit of the 10. So here's another example. Here is a table describing the isotopes and their natural abundances for lithium. And we see that lithium has two isotopes, a lighter one with 6 particles in its nucleus. That unsurprisingly has a mass of about 6 AMU, and that's about 7.6% of all lithium atoms. There is a heavier isotope of lithium with a mass of approximately 7 AMU, and that comprises 92.4% of all lithium atoms. So if I'm going to calculate the weighted average and see what that is, I'm just going to pop up my calculator to do this. Here we go. What I need to do is take the mass of my first isotope, multiply that by its abundance divided by 100, so 0.07594, and then I will add to that the same for the second isotope. So we've got 7.0160040, and again that guy is going to be multiplied by its abundance divided by 100, so that's 0.92414. And just before I press enter, let's think about this. It's 92% of the heavier one and then 7.6% of the lighter one, so it should be a number that's close to 7, closer to 7 than it is to 6. So let's see what we get. And I got 6.94, and that makes a lot of sense to me. Okay. Here's another one. It says there are 2 naturally occurring isotopes of silver, silver 107, which has this mass, and that comprises 51.5% of all silver atoms, and silver 109, which has this mass, and that comprises 48.5% of all silver atoms. So if I think about this, I've got an approximately 50-50 mix of 107 and 109. So I would expect that the average atomic mass would be around about 108, exactly halfway in between those two numbers. So I'll pop my calculator up again, and let's see what we get. So here, I'll just clear that off. So the mass of my first isotope, 106.9, times by its percentage divided by 100, so 0.515, plus the mass of my second isotope, 108.9, times by its percentage divided by 100, 0.485. And I'm expecting that my answer will be halfway in between those two numbers, so it should come out to be about 108. And what I got, 107.87. So I feel pretty happy about that. Okay, So hopefully now you understand how to calculate a weighted average atomic mass. You also understand the idea of what an isotope is. It's important to recognize that the masses that appear in the periodic table are these weighted average atomic masses and are not the mass number of an atom. Okay, so how did we come up with this model for the atom? Where did the evidence for the existence of these three subatomic particles come from? And how did we decide that they were organized with a nucleus containing protons and neutrons, and then electrons orbiting that nucleus? So there were three key experiments that led to the development of this model. The first development was the cathode ray tubes experiments of J.J. Thomson. And what J.J. Thomson had was a glass tube that was coated at one end with a material that glowed when it was impacted by electrically charged particles. Into this tube he inserted a series of metal plates. There was a metal plate at the far end of the tube, and then a little distance away from that is another metal plate with a hole in it. Further along the tube, he has these two metal plates, one that sits near the top of the tube and one that sits near the bottom. At the far end of the tube, away from the coated screen, he connects his first metal plate up to the negative terminal of a battery. So this is negative out here, and then the plate that sits in front of this, the second plate with the one with the slit in it, that guy is positively charged. And what he found when he hooked this up was that he got a glow on his screen at the bottom there. So what that indicates is that negatively charged particles were being developed at this plate. They were being repelled by this negative plate, attracted towards this positive plate, passing through the slit and traveling along the tube and hitting the screen. So his apparatus was producing negatively charged particles. He then used the two plates that were placed near the middle of the screen to study the properties of these particles. He hooked one up to the positive terminal of a battery and the other to the negative terminal of the battery, and what he found was his negatively charged particles were deflected upwards. By varying the charge on these plates, he could move this beam up and down to a smaller and lesser degree, and he had a scale on here, and he was able to measure how far it was deflected. By flipping the charges on these plates, he could get his beam to go down the other direction as well. Thomson knew that charged particles were also influenced by magnets, and he put a couple of magnets either side of his tube. He varied the distance between the magnets, and he monitored how that affected the movement of this beam of negative particles. After doing a bit of math, what he realized was that this beam of negatively charged particles, the mass to charge ratio of these particles was really, really small, a lot smaller than that for any known atom that had previously been measured. However, he doesn't have an exact value for either the mass or the charge of this particle. So Thomson proposes that these rays that he was generating at his negatively charged plate were subatomic particles. These are subatomic particles that we now call electrons, and we normally give it the symbol E followed by a superscript minus. So clearly this is in violation of Dalton's first postulate that said that matter is composed of atoms which are indivisible. So an American scientist, Richard Millikan, he determined the charge on the electron by observing the charge required to levitate oil drops. So what he did was he generated oil drops that had a positive charge. These guys had a positive charge because he had made the oil drop lose negatively charged electrons. he allowed the oil drops to fall under the influence of gravity, but then once they began falling, he would turn on a positively charged plate beneath them, which would repel them. And he would adjust the charge on this metal plate to the point that the oil drop would levitate. By doing this, he was able to figure out the charge on the oil drop. Remember that the oil drop acquires its charge by losing electrons. What Millikan found was that the charge on the oil drop was always a multiple of this number, 1.6 by 10 to the minus 19 coulombs. So he proposed that this is the smallest possible unit of electrical charge. So that is, the charge on the electron is 1.6 by 10 to the negative 19. So as he had the mass to charge ratio from Thomson's experiments, he was able to go ahead and calculate the mass of the electron as well. So using Thomson's data, Millikan went ahead and figured out the mass of the electron. And the mass of the electron is tiny. It's 9.1 by 10 to the minus 28 grams. And this was less than 1/1000th of the lightest known atom, which is hydrogen. So we have fully characterized the first subatomic particle. It's a negative particle with a charge of 1.6 by 10 to the minus 19 coulombs. It has a mass of 9.1 by 10 to the minus 28 grams. So this raises the question, are there more subatomic particles? There must be something that has a positive charge that gives a neutral atom. And as these electrons are so light, what makes up the rest of the mass of the atom? So from these two experiments, Thomson proposes what is referred to as the Plum pudding model. In the Plum pudding model, we have a sphere of positive charge that makes up most of the mass of the atom. And then embedded in that atom, in that sphere of positive charge, are these tiny little light electrons. So that's what's going on, and the important idea is that the density of the atom across the whole atom is approximately the same. It is the same density out here as what it is out here as it is over here. So around about this time, people were discovering that a few atoms spontaneously emit high energy particles. And these particles were given were found to be of two types. There were beta particles, which were rapidly identified as just being high energy electrons, and then there were alpha particles, which were a little bit more mysterious. So what alpha particles are, they are positively charged particles, and they have twice the charge of an electron, so 2 times 1.6 by 10 to the minus 19 coulombs. But they're heavy. In fact, they are 4 times the mass of a hydrogen atom. So a New Zealand physicist by the name of Ernest Rutherford, he had the idea of seeing how do these alpha particles interact with atoms. And what he did was he got his 2 students to set up this experiment. So what Ernest Rutherford did was he got his students to expose a gold foil to a beam of alpha particles. And if the Plum pudding model is correct, where we have an approximately even distribution of matter across the whole atom, these alpha particles, according to his calculations, should go straight through, completely undeflected. So this was his setup. It's called the Geiger-Marsden experiment. We have a box with a pinhole in it with a material that contains a source of alpha particles. So we get a nice beam of alpha particles coming out of this box. We have a gold foil that has been hammered to be just a few atoms thick. So the alpha particles are only going to hit 1 or 2 gold atoms as they move through it. Around our foil, we have a screen that's been coated in that material that glows when charged particles hit it. So when any alpha particles hit this screen, it'll cause a green glowing dot. Now, what Ernest Rutherford was expecting, if the plum pudding model was correct, that the alpha particles would go straight through and they would not in any way be deflected. So we'd just get a single bright dot immediately in front of where the alpha particles were being emitted. It would be no different if the foil was there or if the foil was not there. However, what he found was that a significant number of the alpha particles scattered. In fact, some of them even scattered behind the gold foil. So they must have hit something really, really heavy to deflect them in this way. So this is really important. These alpha particles are very heavy and they're moving very fast. So in order to be deflected, they have to hit something really heavy. It's kind of like if you were firing a machine gun at a piece of tissue paper and every now and then a bullet bounced straight back at you. So Ernest Rutherford explained these results as follows. What he said was that as most alpha particles pass through the foil, the atom must be mostly empty space. Now that makes sense. And then he said as some alpha particles are deflected or bounced back, and then there must be something that is very, very small but very, very dense and that the alpha particles are hitting. Now he did the math and he said that there must be a positively charged nucleus to the atom that contains effectively all of the mass of the atom. And the model that he came up with, the only model that worked, was when we had a tiny little nucleus that is really just 1/100,000th the volume of the atom that contains all of the mass of the atom. But the atom itself has quite a large radius. So he says this nucleus has to be positively charged in order to repel the alpha particles. So you might think of this as being like the nucleus is like a marble in the middle of a football stadium. And then there's a large amount of empty space, but there's something else right out on the edge of the atom. So what's out on the edge of the atom here has to have very little mass, and it has to be negatively charged in order to counter the positive charge of the nucleus. And what Rutherford said this must be the electrons. So what we have now is the planetary or Rutherford model of the atom, where we have a nucleus with effectively all of the mass of the atoms containing positively charged particles that are called protons. And then at great distance from this nucleus, we have these very tiny electrons that are negatively charged orbiting the nucleus like planets around a star. Now, the model of the atom is almost complete, except for Rutherford still couldn't get this nucleus heavy enough in order to deflect an alpha particle. And it wasn't until the 1930s that Rutherford's student was able to finalize the model of the atom with the discovery of a third subatomic particle called the neutron. The neutron is uncharged and resides in the nucleus alongside the protons. So now we have the complete planetary or Rutherford model of the atom, where we have a positively charged nucleus composed of neutrons and protons, and then at great distance from that nucleus we have very small electrons, and they orbit the nucleus like planets around the sun. The neutrons and the protons are very, very heavy in comparison to the electrons, and most of the mass of your atom is concentrated in this nucleus. So this gives us the modern atomic theory. We saw this table earlier. We have three subatomic particles: electrons, protons, and neutrons. Electrons have a negative charge, protons have a positive charge, neutrons have no charge. Electrons have very little mass. Protons and neutrons have approximately equal mass, with the neutrons being a tiny little bit heavier than the protons. So if we break this down into the three key experiments, There were cathode ray tube experiments by J.J. Thomson that resulted in identification of a negative charged particle called the electron. Thomson proposed the Plum pudding model of the atom to explain how the electrons were positioned within the atom. It was sometime later that Millikan was able to completely characterize the electrons' charge and mass through the oil drop experiment. Later on, Ernest Rutherford was able to go ahead and characterize where the positive parts of the atom were, and he did this through the gold foil experiment, which resulted in the discovery of the nucleus. So the nucleus was a positively charged bit of matter sitting at the center of the atom. We now know that the nucleus is composed of subatomic particles called protons and neutrons. So the Rutherford or the planetary model of the atom considers the atom to have a positive nucleus contained of protons and neutrons, and then at great distance from that are tiny little electrons orbiting that nucleus, like planets around the sun, and the electrons are kept in that nucleus, in that orbit due to the attraction between the positive nucleus and the negatively charged electron.